Dear students, in today's topic, we are going to discuss all the important points related to an important chapter called electric current. So let's start from the definition of the current and the way we can measure the electric current. So current is defined as the rate of flow of charges. So the equation I is equal to Q by T. Now this Q can be written as NE by T, where N is the number of electrons flowing through a conductor in a time t second, and E is the magnitude of the charge of the electron. If the rate of flow of charge is variable, then we measure instantaneous current, which is I is equal to dq by dt. That is differentiating Q with respect to time t. Now, whenever an electron revolves in a circular orbit, and as it completes n revolution, electron flows through the same path, and that will result in a current, and that current is given by I is equal to F into E, where F is the frequency of revolution of the electron and E is the magnitude of the charge of the electron. We can even write that I is equal to E by T, where T is the time period of revolution. We can even write this in terms of omega, because omega is equal to 2 pi F. So F is equal to omega by 2 pi. So this is E and omega by 2 pi into E. We can even write this I in terms of E by, where T is nothing but 2 pi R by V, 2 pi R by V, where V is the orbital velocity of the electron and R is the radius of the circular orbit in which the electrons are revolving. So these equations are applicable only to revolving electrons. Only when the charge moves in the circular path, not only for electron, even for any charge we can write it. So in that case, instead of E, I have to replace it with Q, FQ, where Q is the charge which is moving in the circular orbit. So these are all expression for electric current. Whenever current flows through a conductor having area of cross section A, then we can measure current density, which is denoted by J, and the current density is nothing but current flowing per unit area of cross section. That's I by A. Now this I we can also write as N A E V D divided by A, that A will get cancelled and you'll get that as N E V D. So what is N here? N is electron density, number of free electrons per unit volume, area of cross section, charge of the electron, and this is drift velocity, okay, NEVD, because this A will cancel. Now current can also be expressed as J into A. A is a area vector, J is also a vector. So current is a scalar, whereas current density is a vector quantity. So that's why this is dot product of, current is the dot product of current density and area vector. So magnitude wise you can write J A cos theta. Now J is also given by sigma into E, where J is current density, sigma is the electrical conductivity, and E is the electric field inside the conductor. And here E is a vector, J is a vector, therefore we can even write this as a vector form. Vector J is equal to sigma into vector E, which we can even write as vector E by rho, where sigma is the electrical conductivity, whereas rho is the electrical resistivity of the material. So, current is a scalar quantity, whereas current density is a vector quantity. Whenever electron moves through a conductor, they continuously collide with the other electrons, the other atoms, due to which continuously there is a change in direction takes place. So, we can measure the average velocity with which the electrons, they are drifted in a conductor from one end to the other end, and that velocity is called drift velocity. And this drift velocity is inversely proportional to square root of the absolute temperature. But velocity of random motion is directly proportional to square root of the temperature. This is the drift velocity, this is the velocity of the random motion. Now, velocity of random motion is of the order of 10 to the power 5 meter per second, whereas the drift velocity is of the order of 10 to the power minus 3 meter per second. As the electron moves through the conductor, when they collide, we can even calculate the average time interval between two successive collisions, and that is called relaxation time. Relaxation time, which is of the order of 10 to the power minus 14 seconds. So, drift velocity is the average velocity which the electron passes through the conductor, and the relaxation time is the time interval between two successive collisions suffered by the electron. And we can measure this drift velocity. So, Vd is equal to, it's a E tau by m. Magnitude of the charge of electron, electric field, relaxation time, and m is the mass of the electron. Is also equal to I by N A E. Current, free electron density, area of cross section, and then E is the charge of the electron. And I by E is nothing but J. So, it's a J by N into E. J can also be replaced as sigma into E by N into E. So, this is how we can write the various format of the equation called the drift velocity. Now, with the increase in temperature, velocity of random motion increases, whereas the drift velocity and the relaxation time, it decreases. Drift velocity and the relaxation, both, it decreases with the increase in temperature. And from this equation, we can write how drift velocity varies with the area of cross section. So, for a given current, for a constant current, so drift velocity is inversely as area of cross section, which is inversely as square of the radius of the wire. That is, if I is a constant, and for a given metal, that Vd is inversely as A. When current flows through the conductor, it produces one of the effect called heating effect of electric current. And this heat is generated because of the resistance, because of the continuous collision of the free electrons with the other electrons as well as the atom. And the amount of heat generated in a given time is given by H is equal to Vi into T, I square R into T, and then V square by R into T. Potential difference, current, and the time, where R is the resistance of the conductor. Now, here H versus I square. See, H is proportional to I square when R and T are constant. Similarly, in the equation H is proportional to V square here. So, therefore, the graph of H versus I square, not H versus I square, H versus I, the graph of H versus I or V is a parabola, because both the equations here, they are of the format y is equal to ax square. So I'm going to consider two coils. First coil having resistance R1, the second coil having resistance R2. So these are heating coils. Now I'm going to use the first coil to heat a liquid, and a given liquid boils in time t1 when I use the first coil. Next, I'll use the same liquid, and to boil that, the second coil takes time t2. And now if these two coils are connected in series, then the time taken by both the coils in series together is T1 plus T2. So to boil same liquid, now both the coils together, when they are in series, the time T is equal to T1 plus T2. Now if these two coils are connected in parallel, then the time taken will be lesser than the series combination, and the T is equal to T1 into T2 by T1 plus T2. So here what is the T1, T2? T1 is the time taken by T1 and T2, or the time taken by two coils when they used individually to boil a liquid. Then they are connected in series, and now to boil the same liquid. It's important in all the three cases here, 4 cases together, 1, 2, 3 and 4, we have to make use of the same liquid. Then what is the relation between the time taken by the two coils and with that when they are connected in series or when they are connected in parallel is given by this equation. And we can get this equation very easily using the amount of the heat generated, in a coil. Now we can even equate this heat generated is equal to C m delta theta. If specific heat of the liquid is given, where m is the mass of the liquid and delta theta is the change in temperature. So we can even equate these variables of the electricity with that of the property of the material, which is specific heat of the substance or the liquid, where m is the mass and delta theta is the change in temperature when we pass the current, because the liquid is get heated up. So if I consider a conductor of resistance R, across which if a potential difference V is applied with the help of a battery, then a current flows through the conductor, I. A direct current flows through the conductor. And the relation between the potential difference, the current, and the resistance is given by the Ohm's law, which is V is equal to IR. So this is very important relation. You can even remember like this. So V here stands for very important relation. Now I is the current, V is the potential difference across the conductor, and R is the resistance. Now reciprocal of the resistance is given by another quantity called conductance. G is equal to I by R. Resistance is measured in ohm, whereas conductance is measured in terms of an SI unit called Siemen, S-I-E-M-E-N. Okay. Now V is equal to IR. We can even write V is equal to I by G. Now V is equal to IR. V is equal to IR. Or if I rearrange here I is equal to V into G. I is equal to V into G. Now here both the equations are of the form y is equal to mx. In the first equation, m is r. In the second equation, m is g. So therefore, y versus x here, where m is r. So v versus I, the graph of v versus I. It's a linear equation passing through the origin, and the slope here m, which is equal to tan theta, is a measure of the resistance. The slope gives the resistance. And in the second equation, it's a I versus V. I versus V is also a straight line passing through the origin, and the slope is again, which we can take theta, and that slope is equal to tan theta here, and that gives the conductance G. So more slope, more value of tan theta, and more conductance. Here also more slope, more tan theta, and more resistance. So that is how we can find the resistance by measuring the slope of VI graph, and here the slope of IV graph gives the conductance. And the devices which obeys Ohm's law are called as ohmic devices, like galvanometer, voltmeter, ammeter, and the devices which do not obey Ohm's law are called as non-ohmic devices. All semiconductor devices like transistor, diode, then we have pentode, then voltmeter, then superconductor. These are all example for non-ohmic devices in which the Ohm's law is not valid. So when potential difference is applied and when current flows through a conductor, this electric energy is converted into heat energy or in any other form. Now, what is the amount of energy consumed per second? Now, that is called the power, electric power. So, electric power is the rate of work done, which is also equal to I square R, or that's equal to V square by R, that is equal to V into I. P is equal to I square R, V square by R, and V into I. So again here these two equations, P is equal to I square R and P is equal to V square by R. These two equations are of the form Y is equal to A x square. So therefore the graph for both P versus I or P versus V is a parabola symmetric about the y-axis. Now we measure the power in terms of the watt, but we also use some practical unit which is called 1 unit of electricity, that is equal to 1 kilowatt hour. Now this is the unit of electric energy, not electric power, which is equal to 3.6 into 10 to the power 6 joules. Since it is the unit of electric energy and not power, so we get 1 unit of electric energy, unit electricity is given as 1 kilowatt hour, which is 3.6 into 10 to the power 6 joules. Now if we connect bulbs, of 60 watt, if we consider example of 60 watt, and then another 100 watt. So I'm going to connect them in series like this. 60 and 100 watt, they are connected in series. And in another combination, we are going to connect the 60 watt and then the 100 watt. They are connected in parallel. Now, when bulbs having different wattage are connected in series, the bulb with the least rating will glow brighter. So therefore, here the 60 watt will glow brighter. So this is only in series combination. In series combination, if I connect bulbs of different wattage, then the bulb with the least rating, least power will glow brighter. Whereas, whenever we connect bulbs in parallel, so this is our household combination. So there, the bulb with the more wattage will glow brighter. So therefore, out of 60 and 100, it is 100 watt that will glow brighter. So this is a point which you have to remember. In series, low wattage will glow brighter. In parallel combination, the high wattage device will glow brighter. Now, if devices are in in series, okay, if the devices are different devices, if they are connected in series, and if the voltage applied is equal to the rated voltage. Voltage applied is equal to the rated voltage. Now, what do you mean by voltage applied and rated voltage? So, normally along with the bulb, they will write a rating like 60 watt, 220 volt. That means in this bulb works, or it consumes a 60 watt of power when you apply a voltage of 220 volt. If the that is called the rating. If the voltage exceeds the 220 volt, then this bulb will get fused. If the voltage is lesser than 220 volt, then it will glow with lesser intensity or lesser brightness. So that is called the rating. And if the voltage applied across all the devices is equal to the rated voltage, rated is this. So that means in this example, the rated voltage is 220. That means even the applied voltage also has to be 220 only across all the devices when they are in series. Then the effective power consumed, reciprocal of the power consumed in series, is equal to sum of the reciprocal of the rating of the individual devices. This is in series combination. Again, keep in mind that this equation is applicable only when the applied voltage is equal to the rated voltage only. Now, when the devices are in parallel, and if the voltage applied is equal to the rated voltage, then the power consumed in the parallel combination is equal to the sum of the power consumed by the each devices. So this is for series combination, and this is for the parallel combination of the devices, with the condition important that the voltage applied across across the devices is equal to the rated voltage of the device. So resistance of a material or a wire, it depends on its dimension at constant temperature, and that resistance is given by R is equal to rho L by A, where rho is the resistivity of the material measured in ohm meter, L is the length of the material, and A is the area of cross section. Now this is also given by Lm by NAE square tau. The same equation is also given by Lm by NAE square tau, where m is the mass of the electron, free electron density, charge of the electron, relaxation time. So based on this, if you compare here, we get this equation rho is equal to m by NE square tau, which is a constant. So that clearly indicates that the resistance depends on dimension and temperature, whereas the resistivity depends only on the temperature. If the temperature is increased, then the relaxation time also increases. That decreases the resistivity, and decrease in resistivity decreases the resistance. This is how the resistance decreases with increase in temperature. With the increase in temperature, drift velocity and the relaxation time, it increases, that will decreases the resistivity. So resistivity of a material here, correct? Resistivity of a material, and then the resistance here. Okay, 1 minute. So with the increase in temperature, with increase in temperature, resistance increases and the resistivity also increases, correct? Which means the relaxation time, it has to decrease because it's inversely proportional, correct? So let me make things clear here. VD is inversely proportional to square root of T, right? So with the increase in temperature, drift velocity and relaxation time, it decreases, because it's inversely proportional. And decrease in relaxation time increases the resistivity, An increase in resistivity increases the resistance. Correct. So now that is the dependence of resistance with the dimension. Fine. Now we can even write the expression for conductivity. What is conductivity? Conductivity is reciprocal of the resistivity. So that is nothing but N E square tau by M. So here conductivity is directly proportional to the relaxation time. So increase in temperature decreases the relaxation time, that decreases the conductivity. So therefore the resistance increases, whereas the conductivity of a conductor, it decreases with the increase in temperature. Now if I take a wire which is hollow like this, not a solid wire. Suppose if it is a solid wire, then its resistance is given by rho L by A, where A is nothing but pi r square, because area of cross section is a circle. That is for a solid cylindrical wire. If it is hollow, then we have to write the expression for the area of cross section of the solid part, for which let me consider let B be the radius of outer radius and let A be the inner radius. Then resistance of such hollow materials, hollow cylindrical wire, is given by rho L by area of the entire portion, which is pi B square, minus the area of the hollow, which is pi A square. So therefore the effective area is nothing but pi into B square minus A square. So this is the expression for resistance of a hollow cylindrical wire. So now I am going to consider a composite cylindrical wire where it's made up of two different materials. The outer one having material resistivity rho 1, that is the outer cylinder, and then the inner cylinder is made up of a material having resistivity rho 2. And the outer one has radius B and the inner has radius is A. Now what is the effective resistance of this? Now we are going to find the resistance of each material, that is R1 and R2. So for outer material, R1 is, it's a rho 1 and L is the length of both the cylindrical wire by, now what is the area? Area of only the outer one, outer effective. So that is pi B square minus A square, because that is the area of the outer cylinder here, outer cylinder, okay. Rho 1 L pi B square minus A square. Similarly, for R2, R2 is that of the inner cylinder, which is rho 2 L by pi A square. And now these two material, when we apply potential difference across it, it acts as a parallel combination of the two resistances. So therefore, the effective resistance R effective is given by R1 into R2 by R1 plus R2. So this is how we find the effective resistance of two composite wires having different resistivity. Now, what if the material has different area of cross section and there is a direction of flow of current? So let me take A is the area of cross section at one end, and B is the radius of cross section at the other. Then the resistance of this kind of material R is equal to rho L by pi into product of the two radius, which is A into B. Now in this material, I is the same throughout, whereas the current density, which is J, is equal to, it's I by A, correct? See, as the current flows from lower area end to the higher area like this. So A continuously increases, and as A increases, J decreases. So therefore current density is not same. So current is same but not the current density. Current density varies because the area of cross section, it varies at each and every point. So there is one more special case where we are going to consider a wire having resistance R1, resistivity rho, length L1, and area of cross section A1, and radius R1. And this material or this wire is stretched to form a larger length, stretched. And when it's stretched, length increases, area of cross section decreases, even the resistance also changes to R2. But resistivity of the material remains the same because it is independent of the dimension. So the new length is L2, area of cross section is A2, and its radius is R2. And the new resistance R2 is given by R1 into L2 by L1, the whole square. That is also equal to R1 into A1 by A2, the whole square. And that is also equal to R1 into R1 by R2 to the power 4. Because wire before stretching and after stretching, the total volume remains the same. So volume is A1 into L1, that's equal to A2 into L2. So by using that, we can get all this equation. Now if L2 final length is n times L1, if L2 is n times L1, then the new resistance will be n square times the initial resistance. If A2 is NA1, then the resistance here, it decreases n square times. It's R1 by n square, because when A2 is NA1, A2 is here. And if R2 is n times R1, then R2, it's a fourth power there, so therefore R1 by n to the power 4, that is again resistance decreases n to the power 4 times. So these are a special equation used only when a given wire is stretched to form a new wire having different dimension or different length. Now if I take two wires having different resistivity, rho 1 and rho 2, if they are connected in series. Now in series combination, area of cross section has to be same. two wires having same area of cross section, but having different length L1 and L2. So that effective length becomes L1 plus L2. So in this case, what is the effective resistivity of the combination? So rho S is equal to rho 1 L1 plus rho 2 L2 divided by L1 plus L2. So that is the effective resistivity of the series combination. Now, what if lengths are equal? What if L1 is equal to L2? If L1 is equal to L2, this L and this here they'll get cancelled. Thereby you'll get rho S is equal to rho 1 plus rho 2 by 2. So this is nothing but again arithmetic mean of the resistivity, that is when they are connected in series. Now if two wires having different resistivity, if they are connected in parallel like this, so this is one wire and this is another wire, one below the other. Nice. So in this case, in series combination, area of cross section has to be same, whereas in parallel combination, the two material they must have the same length, but different area of cross section, A1 and A2. So in parallel combination, what is the effective resistivity of the parallel combination? That is rho 1 into rho 2 into A1 plus A2 by rho 1 A2 plus rho 2 A1. This is what the format that we get. And the conditional, that is if both the wires are of the same area of cross section, if A1 is equal to A2 is equal to A, and then when we do that here, we'll get rho P is equal to 2 rho 1 rho 2 by rho 1 plus rho 2, and this is nothing but the harmonic mean of the two resistivity. So that is the combination of the resistivity or combination of the materials having different resistivity in series and in parallel combination. Now with the increase in temperature, the resistance of the material increases. So that we can explain using R is equal to Lm by N A E square tau. With increase in temperature, relaxation time and the drift velocity decreases, that increases the resistance. Now in a conductor, this is applicable only for conductor. In conductor, the resistance increases according to the equation RT is equal to R0 into 1 plus alpha T, where alpha is called temperature coefficient of resistance and R0 is the resistance at 0 degree and RT is the resistance at T degree centigrade. Here T is the temperature and unit of alpha is either per degree centigrade or you can even express in terms of per Kelvin. Now for two different temperature, and again if you rearrange this equation, you will get like this: RT is equal to, if I open the bracket, I will get R0 plus R0 alpha T. Now this is of the format y is equal to mx plus c. That is the graph of y. Y is here nothing but RT, and x is this, which is T in degree centigrade, and there is y-intercept which is positive here, and the value of which is R0. So it's a linear. This is what you get. And then what about the slope of it? The slope is this R0 into alpha. And if you want to find alpha, so alpha is nothing but slope divided by y-intercept. The slope by y-intercept gives the value of alpha. the slope is R naught alpha, divide by R naught will give you the value of the alpha. Now at two different temperatures, alpha is also given by R2 minus R1 by R1 T2 minus R2 T1. And what is important here is whenever you do the substitution in this equation for T, it has to be in degree centigrade only. So even here when you do the substitution for T1 and T2, it has to be in degree centigrade only. Now if the difference between T1 and T2, okay, that is T2 difference at T1, if it is very small, then we can write the equation alpha is equal to R2 minus R1, R2 minus R1 by R1 into T2 minus T1. So this will give you the approximate value of the alpha. So this is the equation which will give you the exact value of alpha, but if the difference between T2 and T1 is very small, then you can even go for the approximate equation. So alpha is a temperature coefficient of resistance that is also equal to, what is R2 minus R1? That is change in resistance to the initial resistance. That will give you the fractional change in resistance. Fractional change in resistance to the change in temperature. That is fractional change in resistance per degree centigrade rise in temperature will give you the value of alpha. Okay, fractional change in resistance per degree centigrade rise in temperature will give you the value of alpha, which is per degree centigrade or per Kelvin is the unit of the alpha, which is called TCR. So lesser the value of temperature coefficient of resistance, smaller is the variation of resistance with the temperature. So that's why in making standard resistances or standard resistance boxes, so material having low value of alpha are preferred because the variation of resistance with the temperature is very less or very small. So that is the advantage of the material having smaller value of temperature coefficient of resistance. So just like finding effective resistivity of materials in series and in parallel, we can even find the value of effective value of temperature coefficient of resistance when two wires having different value of alpha. One material or one wire has alpha 1 as temperature coefficient of resistance and the other material has a value which is alpha 2. They are connected in series. And let R1 be its resistance at 0 degree centigrade and let R2 be its resistance at 0 degree centigrade. Then effective value of alpha, that is effective value of temperature coefficient of resistance in series combination is given by alpha 1 R1 plus alpha 2 R2 by R1 plus R2. So that is the effective value. Now, if R1 is equal to R2 at 0 degree centigrade, if they are different, then we have to use this. If they are same, that initial resistance at 0 degree are same, then we get alpha S is equal to alpha 1 plus alpha 2 by 2. So this is conditional equation only if they have same resistance at 0 degree centigrade. Now if I take two wires connected in parallel, so one material having alpha 1 as the temperature coefficient and the other having alpha 2 as temperature coefficient of resistance, and then the same condition, that is R1 is the initial resistance at 0 degree centigrade and R2 is the resistance at 0 degree centigrade, then the effective temperature coefficient of resistance in parallel combination is given by alpha 1 R2 plus alpha 2 R1 by R1 plus R2. So here also, if R1 is equal to R2 at 0 degrees centigrade, if they have same resistance at 0 degrees centigrade, then alpha P is equal to R1 plus R2 by 2. So we get the same equation in series as well as in parallel combination if the resistance of the two wires are same at 0 degrees centigrade. Otherwise, their effective temperature coefficients are different in series and in parallel combination. So now let's learn everything about an important circuit called a simple circuit. Now, what is exactly a simple circuit? A simple circuit consists of one resistor, which we call external resistor, and then a battery or a cell having EMF E, and then internal resistance R. The current through such circuit is called the main current, which is I, and across the resistor, whenever there is a flow of current, there exists a potential difference, which we call the terminal potential difference. Now, first, what is the current through such a circuit? The current through such circuit is given by I is equal to E by R plus R. And if the internal resistance is neglected, negligible, we'll specify in the statement that a cell of negligible internal resistance. In that case, we take R0. So, in such case, we can write I is equal to E by R. What is the potential difference across the external resistance, which is also called as the terminal potential difference, which is a V is equal to, we can measure it using the Ohm's law, that is I into R. But I is nothing but E by R plus R. So, we can even write I is equal to E by R plus R into this R. And this V also given by E minus I into R, where IR is the potential difference across the internal resistance, or the loss of energy that takes place due to internal resistance is minus I, R, or I into R is the PD, or we call potential difference across the internal resistance. So, this is called the terminal potential difference. Terminal potential difference. And this equation we can even write like this. It is E by 1 plus, if you divide by R, you will get E by 1 plus R by R. That's. Now, based on that, we can write few terms. That is, if the circuit is an open circuit. Now, what do you mean by an open circuit? An open circuit is one in which there is no flow of the current. Why there is no flow of the current? Because an open circuit, it acts like a circuit which offers infinite resistance. And you can see here, if the resistance is infinity, reciprocal of the infinity will give you zero current. So, the value of current is 0, I is 0. And when I is 0, from this, when R is infinity, this term becomes a 0. We will get E by 1. So, that is why V is equal to E. That means the terminal potential difference is equal to the EMF of the cell when the circuit is open. So, that is called open circuit. Now, we have a closed circuit, or we can also call it as a shorted circuit. Now, what is a closed circuit? If the cell is shorted itself, then R is a 0. So, here without connecting the resistor, if the cell itself is connected like this, to itself. That is called short circuiting the cell. Okay. Then R is 0. And when R is 0 here, reciprocal of 0 will give you infinity. And this term becomes infinity. And again 1 by infinity becomes 0. So therefore the value of V becomes 0. And here when R is 0, the current will be I is equal to E by R. I is equal to E by R. So what we get to notice here out of these two cases is that in an open circuit, current is 0, but the voltage is maximum. And in closed circuit, the current is maximum, whereas the voltage across that device or the voltage across that resistor becomes 0. 0 current, maximum potential difference, and maximum current, 0 potential difference. For this equation, V is equal to E minus IR. So if I have to draw the variation of the voltage with the current, V is equal to E minus IR. Then this equation is of the form Y is equal to minus mx plus C. Minus mx, that means the slope is negative. It's a straight line, but the slope is negative. So this is the kind of graph that we get. So here x is I. So therefore the value of the slope is equal to the internal resistance. So m is equal to R. And the value of the y-intercept here is E. So that is the kind of the graph that we get when we draw V versus R. Fine. Now, we can even draw graph of V versus capital R based on this V versus capital R. So let us substitute like this. When R is 0 and when R is infinity, what is the value of V that we get? Check this here. When R is 0, reciprocal of 0 becomes infinity, and again reciprocal of infinity becomes 0, therefore the value V is 0. But when R is infinity, reciprocal of infinity becomes 0 here, V becomes equal to E. V becomes equal to E. So therefore, when R is 0, V is 0, the graph starts from the origin. And then as R increases or as R tends to infinity, V tends to E. So this is the kind of the graph that we get. So it becomes parallel to the R axis because R is infinity. So we get a parallel curve, and then here this is that value where V becomes equal to E. So this is the variation of the terminal potential difference with the external resistance. So in the same circuit, we can even find the power consumed, power. So what is the power consumed? Power is given by P is equal to I square R. And the value of I is nothing but E by R plus R. So therefore it is E square by R plus R the whole square into R. So that is the power consumed. Now this power consumed becomes a maximum. The power consumption is maximum when the internal resistance is equal to the external resistance. When R becomes equal to R, the power consumed becomes a maximum. So if I substitute here, if R is equal to R, so I'll get 2R here. 2R the whole square is nothing but 4R square. And again there is one more and that will get cancelled, giving P is equal to E square by 4R. So this is the maximum power consumed in a circuit, and that happens only if the internal resistance is equal to the external resistance. And the kind of the graph that you get So this is the power versus the value of the internal resistance. And the power consumption increases and then it becomes a maximum and then further decreases. And here this is that P max value, P max, and that is when R is equal to capital R. That is, internal resistance is equal to external resistance. The power consumption is maximum. During charging of a battery. So this is the external battery that we have used with an internal resistance R. So this is the EMF, which is E, and here this is the cell that is to be charged. Normally in a circuit, when we connect a cell to a resistor, so resistor always it draws current from the cell, from the given cell. And now during charging, the flow of the current is exactly opposite because this battery has to charge this particular cell. So this is the charger, charging device. Okay, this is the battery that is to be charged. Therefore, the direction of the flow of current is exactly opposite. So here the current is drawn from the cell, correct? And here the current is drawn from the device which is to be charged. Thereby, the terminal potential difference across this device will be E plus IR. So here V is equal to E minus IR. Correct? It's V is equal to E minus I whenever there is a flow of current. But during charging, because of change in direction of the current, it becomes V is equal to E plus IR. And here if I have to draw the graph, then I'll get Y is equal to Mx plus C. So this graph, that's a V versus I. V versus I is current here, is a straight line, not through the origin, having y-intercept that's equal to E, and the slope is equal to the internal resistance of the charger that we are using to charge this particular battery. So these are the equations pertaining to the simple circuits. So we have a device called potentiometer. A potentiometer is a device which is used to measure EMF of the cell. And in this potentiometer, we have the standard cell, which is also called as the primary cell, which is connected to a potentiometer wire. So this is the potentiometer wire having resistance capital R. And then we connect the cell whose EMF is to be measured, and with the help of the galvanometer, we measure the length, which is called as the balancing length, at which the galvanometer shows zero deflection. Now, if E1 is the EMF of this cell and R is the internal resistance that is to be measured, then we measure what we call potential gradient. Potential gradient. So how to measure the potential gradient? The potential gradient is nothing but it is the potential difference per unit length. Now what is the potential difference? Potential difference is nothing but ER by R plus R into L, where E is the EMF of the standard cell, okay, and R is the resistance of the potentiometer wire, and R is the internal resistance of it, okay, and L is the total length of the wire, total length of the potentiometer wire. Now here the EMF of the cell to be measured is directly proportional to the balancing length, and that's why the ratio of the EMF E1 by E2 is equal to L1 by L2. This is for two different cells. E1 by E2 is equal to L1 by L2. We can even measure the internal resistance of the given cell, which is R is equal to capital R, which is the external resistance to be connected here with the help of a resistance box. R into, it's L, or I'll write L1 minus L2 by L1, where L1 is the balancing length when this resistance box is in the open circuit, and L2 is the balancing length when the resistance box is in the closed circuit. So therefore, the main use of the potentiometer is one, comparison of the EMF of the two cells, and the other to find the internal resistance of the cell. Now using the potentiometer, you can even find the ratio of the EMFs by connecting two cells simultaneously. That is, we connect the cells in series, and then by connecting the same cells in the reverse polarity. So here E1 plus E2 is directly proportional to the length L1, and here E1 minus E2, where E1 and E2 are the EMF of the two cells. E1 and E2 is directly proportional to L2. So that the ratio of the EMFs, that is E1 plus E2 by E1 minus E2, will be equal to L1 by L2. So by connecting two cells together, we can find, so from this we can find the value of E1 by E2 very easily. So where E1 and E2 are the EMF of the two cells. So we are going to learn more about this chapter in the next session. Thank you.